So the biggest and hardest and most important concept, I would say, for binary translation systems, which are system level translations, is having to maintain precise context.
Hello and welcome to Nitty Gritty Talks, and today we're discussing the cornerstone of dynamic system level optimizers, which is precise context, and specifically the need for the translator system to be able to present it at any arbitrary point of program execution. And that is exactly the cost that translator has to pay in order to be able to achieve its goals, as discussed in previous video. If you are new to the series, as usual, I will leave a link to start the series from the beginning. That's the way I recommend watching this. And now let's go back into the presentation mode. And precise context means that the existence of dynamic optimizer system should not be visible to the code that is running on the source architecture, which is not being translated. In practice, this means that we should be able to present the state of things, how they would be in the source architecture if there was nothing underneath. So basically, state of the registries, state of memory, state of external devices.
So how do we approach that? Of course, we can do per instruction basis. So for example, we have one set of instructions in the actual hardware underlying, we have different set of instructions. And we want to translate one set into the other. And we can take the instruction, for example, A equals B plus the value from memory address. So load with summation. And we don't have this instruction. We could just translate that into load and calculations. And we even have can have stack-based architecture with just one or two registries. So yeah, we could handle all that, but for each instruction in the initial workload, we will have 3, 4, 5 instructions. It will make things very bad, especially for system calls, interrupts. It will be a mess. And what can we do differently? We can take a lot of instructions, translate them like this, and then try to do something with it. For example, we had we can have arithmetic optimizations. We have a equals a plus 5 10 times, and then we can, like a regular compiler, just to do something with it. Or we can have some additional things which were not recognized. But the question is, how do we maintain precise context? And the solution to this brings me to a point
that relational database engines are not too far from the dynamic optimizing translator systems. And now over to you. Why do you think they are so similar?
The solution to this is having a transaction. So we group the instructions into specific sets, which are called optimization interval, and we can optimize and rearrange instructions within this set as we want to. We can do beautiful stuff. We can speed up, do analysis, anything. But we cannot mix instructions between optimization intervals because it would break the idiom of precise context. We don't want the context to be maintained per instruction basis because it's too expensive. But we are guaranteeing this on like checkpoints, like at the points of transaction, which it is done. But if we have system interrupt, for example, in the middle of optimization interval, we have to restore this precise context in the middle. And what we do rollback, and then we have the backup mechanism, which does per instruction basis for specific this case, which is called recovery. And then we go per instruction base to the middle of the interval, and then say we are ready for system interrupt. We have this precise context and we are ready to continue. And it's a huge limiter to optimizations, as you already mentioned. So you cannot allow to have x86 into itself translation on like general CPU and have system level translation on top of it. It would be very, very expensive. You would want your architecture to be somewhat specific to the setup that you want and to have some support, some hardware support. Yeah, for example, you want to do transaction, you want to have backup. For example, you want to have a registry file backup in order to do fast rollback. For example, the interrupt comes, you don't want to copy 64 registers one by one in order to restore that state. You want to do it in one block, preferably. And this hardware support is also difficult. You have to own a whole stack. You have to be a hardware engineer company in order to do that.
And before we conclude, I suggest to look back at what we learned today. One of the main challenges and the limiters for dynamic system level translator is the necessity to provide precise context, specifically at the points of system interrupts. Also, we covered high level how to achieve that. The system breaks translated code into chunks and makes a checkpoint in between each chunk. Also, it has a mechanism to make a fast rollback to the latest checkpoint, and after that, switch to a different translation mode, which executes the source architecture instructions one by one, until the point of failure and further. So that will be it for today. Thank you very much for your attention. And the next time we'll discuss my favorite part, examples of the things that the translator can do with the code in order to make it execute faster. I would be able to make it more interactive and provide you a kind of puzzle vibe here. So that would be fun, and stay tuned for that. I will see you there.